afternoon. We're Shasta High School. I'm Adam Zupon.
And I'm Reba Mosen.
And we're going to start our talk on ancient number systems. You already know.
One important thing about number systems is that they change when we change. And the more mathematical needs we have, the more advanced we need our number systems to be. So imagine that you have a flock of sheep, and you need to keep track of how many sheep you let out in the morning and how many sheep you gather back at night. If your flock is small, you can remember all the sheep by name.
So you could potentially name them like Larry, Curly, and Mo, and Bill and George and Barack. But as your flock slowly gets bigger,
it's much more difficult to remember them by name. So what you can do is use a number system. For example, you can use twigs or stones to represent the sheep, and one by one you can transfer them from one place to another as the sheep leave.
and that's the basis of a primitive number system, which we see in the Mayans, which really used that.
The Mayans started with a representative system using physical objects like twigs and stones, but the Mayans had a large empire and needed to be able to record and transport larger numbers, which were difficult to keep track of using just pebbles. And so they moved to a written system.
Exactly. So you can really see the beautiful example that a dog is literally the cocoa bean, which is their currency, or a stone, or that one twig, the line really represent the next highest unit. You just kept going. What's nice about the Mayans is they actually began to understand a zero as a placeholder and form a positional number system. And so as they moved up, they could represent larger numbers with fewer symbols by having that base 20, which was started 20 digits on your fingers and toes. And so you can really see that transition from they were counting physically, they transferred it into a written system because they had a need to transfer that information across a great empire. And actually, what's interesting about their zero, some people think it looks like a shell, other an empty bowl, but really it's just a depression to show that nothing's there. My own theory would be that they had sheep, and then suddenly they had no sheep, so they tried to represent what caused no sheep to be there. What's the zero? And the next more complicated number system.
The Egyptian system was also representative, but it was more symbolic. And each unit of 10 had its own specific symbol, and the larger the number, the more symbols used. For example, the number 50 would be represented by 5 of the 10 symbols.
And it's still very physical, like they were drawing things they were familiar with, like one. I mean, either a finger or a staff or whatever you want to call it. Next highest gets a little more complicated. 5 million, that's just wow. So, but they were also limited. Obviously, they couldn't go over 10 million because they didn't have another unit. But that satisfied their need for the engineering they were doing, taxation, dividing salaries, all of that could be done with this number system. But again, it could get really big if you wanted to represent 999, you need 27 symbols. And so it was gradually replaced by the Greek system, which is much more modern.
The Greek system is more modern because it has abstract symbols and specific notation to represent different numbers. And it wasn't exactly positional, but the Greek system led into the positional system that we have today.
Yeah. So they continued that format in which they went from highest to lowest. But as you can see, they had 27 different symbols, which made it, you could write a 8091 or 80901, and that would be the same as a 981. So it would just be like misspelling almost, which also that was the same as their written language. So it wasn't totally unique, it's a bit more abstract. So they are gradually progressing to kind of philosophy and abstract thinking that they could do. So just recap, Basically, it's how efficient is your number system at meeting your needs. The Mayans, they didn't need to do much, but they actually did a rather good job with their lines and their dots and their base 20. The Egyptians, as you can see, even in this smallish number, needed a lot of symbols. So it was replaced by a very compact Greek, but you can also tell how it could be confusing with all the symbols. You need to memorize all 27, even 28 with a big M. And so my addition is pretty simple. You'd add across all of the units, and then you simply have to go in and change them to the base 20, or to the next highest unit. So 5 dots make a line, so get rid of those 5, and add another. Now, make 20 the next unit up, that'd be 4 times 5, 4 lines, and you get another 20 dot. Repeat this, and you gradually get what the actual answer is in correct notation.
You can see how that's similar to what we do today in math. If you were to add, say, 19 to 27, and we carry the 1, instead of, then you would have to carry the 10 over again. So,
Exactly.
similar.
But we have less symbols, so it's easier for us to see the relationship between the final answer and the next, which brings us to a modern system like ours.
Our modern system has all the aspects of these number systems. It has symbols and positional value and the number 0, obviously. And this makes making recordings and calculations much more efficient and much less time consuming.
So, which allows us to have the great math-based society we have today. I mean, it's not only for scholars, it's not only for accountants, but everyone who needs to find out how many eggs go into a cake, how many miles to gallon they get. They can all use these numbers because it's both compact enough to be able to be done quickly, but also simple enough and uses its position in a bigger number to optimize the actual size and physical space taken up by the number. And so that is why we've taken the position and the baseness from the Mayans. We've taken the compact multiple symbols from the Greeks, but refined it to our own to produce something that is the best of all of them, and again, can meet all of the needs of our society. So what will be coming next?
As we have more mathematical needs and we expand upon what our math is capable of, we would need to adjust our number system or possibly have a whole new number system to meet those mathematical needs.
Exactly. So like the computer, I mean, it's great, it's revolutionized, you could say, but we need to talk to it in its own language, so we made binary, which you will never see someone on the street counting binary out. It isn't efficient in that manner. But in a computer where you have either on or off, you can do that. Like hexadecimal, sometimes we have giant numbers in a computer or elsewhere, and we need to kind of squeeze it down so it doesn't take up as much space. Hexadecimal, like that 5-digit 15,000 number, you only need 4. That's just on a small scale. And so gradually, as our needs change, as math changes, we're going to need a better or different number system. And so that's where all of us come in, that as future mathematicians, we're going to be the ones that will be creating this, refining it, and getting the